Hello, everyone, and welcome to essentially our wrap up of describing simple mixtures. So, today we're going to be tackling that rather messy concept of ionic mixtures. So, essentially, what's going to start happening to some of our equations, especially those of free energy, when I start dealing with the fact that some species tend to kind of break apart. And this is one of the things that actually really makes ionic systems so much different than everything else. And this is the fact that they decompose into interacting solutes. So now I really have to worry about the interactions in between my various in between my systems because my solute A splits into half, so I've doubled the amount of solute present, but also B, those solutes aren't going to interact uh, as an ideal solution because there's a significant amount of IMFs, but they don't even interact as a regular solution because they'll tend to clump into ionic pairs. So this is going to become rather troublesome to try and address. So let's go ahead and start by looking at one of the simplest versions of an ionic compound, which is just going to be a simple salt of a cation and an anion where they both have the same charge, and so this gives me a one-to-one mixture of everything. So in this case, what I can do is say, well, let's figure out how this behavior would work ideally. So if I don't have to worry about any of those intermolecular forces as just kind of a starting point. And well, in that case, I have to deal with the fact that they are still going to break apart. So I'm going to have the potential energy for my cation and the potential energy for my anion. And of course, they're going to have an associated concentration. So in this case, my cation can be described by its chemical potential plus the correction factor based on its mole fraction, and the same thing for the anionic component. Now what we have to deal with is the fact that I need to address all of the factors of this uneven form of interaction. And I can do this with activity. Because what I can say is that the chemical potential for my real cation is actually going to be this ideal chemical potential plus a correction factor based on the activity coefficient, which we talked about last time. We can do a very similar trend for the anion. So thus what we can do is embody all of the ionic character in one simple correction value. Well, two simple correction values, the activity coefficient for the cation and the activity coefficient for the anion. Well, let's be honest, we could go ahead and then use the log laws to combine these of the natural log of RT of the natural log of the activity coefficient for the cation times the activity coefficient for the anion. And that's actually, in general, what we're going to do, is we're going to replace the activity coefficients for each individual species with instead a more or less a combined activity coefficient, which is going to represent a combined form of the activity coefficients of each of the species individually. So this is more or less going to be our average or mean activity coefficient, which lets us describe the non-ideal behavior of the entire ionic species with one simple value. However, one of the things we have to watch out for is this assumed a simple salt with a one-to-one ratio of the two components. So what's going to happen if I've got a more complex salt where I have to deal with the fact that I may have more of my cation than my anion, and again, all of this will be based on different atomic charges. Well, in this case, I can apply some of the same basic principles. So now when I'm looking at the chemical potential of the entire complex, I have to deal with the fact that I'm going to have P moles of my cationic complex per mole of the whole complex, and Q moles of the anion per mole of the whole complex. And this is going to essentially carry through when I describe the chemical potentials of the individual components. and the related activities. So when we end up doing this, we can go ahead and combine this into our ideal component and our combined non-ideal component. But again, now I have to watch out for the fact that I'm dealing with a combined feature of the activity coefficients of my cation plus my anion when I'm replacing that with my average activity coefficient. And so what we do is again make a make a replacement where our activity coefficient for any given molecular species is going to be given by the amount by the activity coefficient of the cation times its stoichiometric coefficient times the activity of the anion times its stoichiometric coefficient, all raised to the power of 1 over the total number of ions. So essentially what this does is again help us average out the system. So if I say have a 3-to-1 ratio, we're going to find the activity coefficient is going to be more heavily emphasize the more abundant species. And this is actually going to be a very good way of essentially trying to give us a free energy for the entire solute complex for most low concentration species, because we are making some assumptions to the extent of the ideality. And again, sometimes you are going to be determining the activity coefficients of each of the individual components, and so you can just generate the average from the geometric mean of those independent values. But this, unfortunately, leads us to one important question. In order to be able to describe the free energy of these ionic species, we are going to need a way to determine any of these forms of the activity coefficients. So this is going to be where we really need to focus. And we can use some logical ideas about the behavior of ionic species. First, we have to think about how the ionic behavior is going to change our chemical potential and thus the activity coefficients. Well, what I have is I've got a cation and an anionic species, which are going to experience a certain degree of interaction. And this interaction is largely driven by attractive intermolecular forces. So I'm going to essentially see a certain tendency towards these species spending more time interacting with each other and less interacting with the greater surroundings. And so what this is going to do is generally lower our chemical potential because I effectively have a lower concentration of ions than I would expect because they don't want to interact with the outside world quite as much. And so we're going to need essentially a feature that kind of demonstrates this decreased interaction. And so if we're dealing with fairly low concentrations, we can use what's called the Debye-Huckel limiting law. So this is going to be a way of describing our activity coefficient through a log function as a function of several key behaviors. The first is going to be the ability of our solution to conduct charge. Because if I'm in a solution that is a really good insulator, well, these species may as well be ideal because they won't really interact with each other. However, it turns out that water is a pretty good conductor of charge, and so is a fairly sizable value for A. The next up is going to be a sheer measure of the charge of the individual ions. The greater the charge, the more likely they are to interact. And finally, the ionic strength. So this ionic strength is really just a measure of the concentration of our charge in solution. So the more charged ions I have, and again, the greater their charge, the more likely I am to see these large interactions binding the system together and decreasing the net chemical potential or activity of the system. However, we should be able to figure out our value for A and the charges by clear inspection, at least if we're in water. But this leaves one major component that we need to try and determine. and that's the ionic strength. So again, our ionic strength is more or less just a form of ionic concentration. So what we can do is we can obtain this value more or less by taking a sum of the molality of each of our components divided by essentially a normalized molality, in this case, 1 molal, essentially as a form of unit annihilation. And then we're going to multiply this by the charge of that ion squared. So again, the greater the charge, the much greater the import of that ion. And then we'll add this up for each of the individual ions present in solution, and then divide by uh, 2. And this is going to be the effective ionic strength of our solution. So for example, if I'm dealing something like a 1 molal solution of sodium chloride, each of the individual ions is going to have a concentration of 1, multiplied by 1 squared, which is still 1. Add those two ones together, I get 2. Divided by 2, I have an ionic strength of 1. So in this case, a 1 molal solution of sodium chloride behaves with an ionic strength of 1. Now, you may notice that this may be quite an exception, but it gives us a simple case, but it gives us a good starting place to describe a more complex ionic system. However, in many of our cases, we're looking at binary salts, so we do have a rather simplified form of cation times cationic charge squared plus anion times anionic charge squared divided by 2. And again, the big thing is all of this assumes concentrations of molal, and so we're just going to be normalizing for units. However, one of the things to watch out for is that, again, the Debye-Huckel only works under fairly low concentrations. As we extend our system, we start running into some nonlinear behaviors. And so we're going to have to do the classic PChem approach, which is tack on a correction factor. So one of the simplest forms that we can do is by going to what's called the extended Debye-Huckel law. So it's taking this Debye-Huckel form in the numerator, and then we're essentially just correcting the denominator by a factor of B, which is going to be a measure of how close our two ions can approach. The closer that and this is what this is largely going to help demonstrate is that under high concentrations and where the ions aren't able to approach very closely, they're going to more or less have the same equivalent of what we'd see with a van der Waals gas, where we're occupying real volume with that charge distribution. So I can't pack my ions quite as closely together as the simple Debye-Huckel law would predict. So in truth, my activity coefficient will be a little bit higher than predicted by the simple Debye-Huckel law. And again, this approach does a pretty good job of getting us to slightly higher concentrations. But again, at a certain point, even the extended Debye-Huckel law will start failing, and we'll need to keep adding in extra empirical corrections. And so by adding a final term based on a C parameter and the ionic strength, we can go to what's called the Davies equation. And this gets us to slightly higher concentrations of being able to describe the system. But one of the things that I really want to emphasize about both the extended Debye and the Davies equation is this requires known empirical parameters. So unlike the simple Debye-Huckel law, which is fairly universal in its application, in this case, you need to know a lot about your solute, which you may not always have. And so it can be sometimes very important that you can find a way to obtain these values independently. And at this point, we start getting into some of the details of how to describe the activity of a system and ionic strength that we go into a little bit more detail during during analytical chemistry. However, one of the things I do want to emphasize is that, again, all of these equations tend to break down under extreme ionic strengths. And so, again, what we see is the real behavior starts showing kind of this uh, curve behavior. As I go to increased ionic strengths, I'm going to have more forces, not allowing me to have, say, an activity of zero, as we saw with just the fact that real ions take up real volume. And so in practice, what we end up finding is that the bihuckle is generally only going to be good for molalities less than about 5 millimolau, whereas the extended bihuckle can actually start getting you much further, up to concentrations about 1 molau. And then once we go to the Davies equation, it almost can usually get you up to about 0.5 molau. But unfortunately, once you get past about 0.5 molau, most of these ionic laws do tend to break down fairly universally. And so at that point, we're almost better off by trying to actually go back to where we started and trying to describe the solvent system, and then working backwards, saying, if I know the chemical potential of the solvent, I can use this to gain some information about the chemical potential of the solute I'm working with. And this can often be done through such measures as colligative properties, or simple measures of vapor pressure. So next time, we're going to start a new topic and looking a little bit more at complex phase diagrams for mixed species. Until then, take care.